we are already behind. We are not falling behind, we are already behind. So, young people, in the instantaneous center of zero velocity topic, before you find all of the instantaneous center, it is difficult to exactly say which instantaneous center you are going to use to determine the velocity. So this is why always all the instantaneous center need to be found first, and after that, looking of the instantaneous centers that you determine, based on that, you need to develop a strategy. How can we find the velocity of the required links? So, for example, in our assignment, in the assignment as well, in our problem, that problem number 2 we are discussing, our objective was to find the velocity of the, don't worry about all this line at the moment. Your objective was that the velocity of the link 2 is given, either rotational velocity or the linear velocity, doesn't matter. Because if the linear velocity is given, it is a VA here. And if the rotational velocity is given of the link 2, that will be omega 2. And your dimension of the OA will be given. So therefore you can find the VA equals omega 2 times ROA. So either way you can find the velocity. Clear to everyone? And our objective in this particular problem is to determine, when our VA is given to us, what will be our velocity of the slider 6 or the piston 6 or the link 6. Clear to everyone? And for that, to determine that, we found 8 instantaneous center. 8 instantaneous center we found. The question is, do we need all 8 of them to find our velocity at point C of the link 6? This question extremely difficult to answer before we find all the instantaneous center. That's what I'm saying. So remember, we found, look at there, we found all the instantaneous center. You can clearly see it here, I13, I36, I24, I26, I35, I35 is here, I46 is here, I25 is here, I15 is here. All this instantaneous center we found in our system. But we really need all of them to find the velocity of the piston 6. We don't need it. And I show you how. So first of all, look at here. Our object, don't worry about this one first. Look at on this one. And this particular one, we have I23 here. Look at here. Our VA, the velocity VA belongs to the piston and the crank, which is connected at that point. At that location is our VA, which is a 9 meter per second. It could be any value 6 meter per second or any other things. So now, and link 2 and link 3 has a connection here, right? On the other hand, our objective is, based on this velocity, to find our link 6 velocity. So how we will be developing our strategy, which instantaneous center we will be going to use and which one we are not. So for that, it is I always call a climbing a tree. I'm not sure how many of you try to climb a tree, but when I was a little boy, I was very naughty. And I tried to climb on a various type of trees, and sometimes I fall. Luckily, I still survived. One time I actually fall very high up, but luckily the soil was marsh, water and the mud together. So that's why I fall it on there and I survive. Otherwise, Firozaram would be somewhere else. Okay, so but the problem is how you climb the tree. You always find you hold one branch. Look at here how I do. You hold the branch and then you try based on that branch on the left hand, you try to catch the right hand one, right? Nearest one. And then you move on to the that one, and then again you hold on that one, you move on to other one. Or vice versa. Those who are left-hander, you most probably going from right to left. Doesn't matter. So it is sequential. There is a similarity with our dynamics as well. Dynamics did not come all of a sudden from the sky. It is a logic. So our objective is to find the velocity of link 6. Look at here, link 6. So we need to find some instantaneous center that has a connection at least with the 5. Is it clear to everyone? And then that 5 should have connection with link 4 or link 3. We can skip one. You know, sometimes when you climb on the tree, you want to hold the next one, but another branch could be next to you. You skip that one, you put the other one, which you can jump there, right? Exactly the same scheme, same system. So again, I draw your attention because it is not written in the book. I don't understand. Sometimes you don't put attention. It is extremely difficult topic. When you talk about the instantaneous center of zero velocity, I found even at RMIT, when I talk to some academics, they are running away from me. They said, Firoz, please don't ask us these things. And that's why I am, unfortunately, the subject that I started to teach in 2002, I am still there. I cannot take a break, I cannot take a holiday, I cannot take any conference I can go between the semester because I cannot find any replacement teacher to push it. And if I ask them, they will be doing not the thing that I teach in the student. So this is why you are little bit, I'm not saying you are lucky, but you are a little bit fortunate in one sense that I am here to sharing my knowledge of this subject that you do not find in the book. Okay? That is an important thing. In Melbourne, if I say that I am going to Singapore or Hong Kong to teach my 300 students, they immediately will say in one word, I wanted to give some other replacement teacher to send. Even my PhD student, they in one word say no. We will be waiting for you. We will have an alternative class. When you come back, you tell us when you are available, we will attend that class. This is the reason. It is not that I teach super, no. But I always try my best to complex concept to tell you the way you understand it. Simple way. So now have a look. As I said, our objective is to find the velocity of the link 6. Only the input velocity given to us of link 2, which is VA. Clear to everyone? So we need to go, we are at the root of the tree, we need to go somewhere on the top of the tree here. Clear to everyone? So now we need to go sequential. So what do? We need to find our instantaneous center that has a connection with the 2 or 3 or 2 with 4. Clear to everyone? And then either 3 with the 5 or 4 with the 5 and then 5 with the 6 we have a connection. Then we can move on. Clear to everyone? So if it is, look at very carefully. We have instantaneous center. One we have I13 here, we have a 3,5 here, and we have a 1,5 here. Can you see? They are in the one line. Let's go to see where it is in our instantaneous center. We found few seconds ago. Hey, look at here very carefully. Did we find I13 here? Did we find I35 here? Did we find I15 here? They are one beautiful red dotted line. That line is the radius of the instantaneous center. On that radius of the instantaneous center, 3 instantaneous center lines. 1, 3, 3, 5, and 1, 5. And then I15 belongs to the radius of the instantaneous center I16, which is passing through I56 and also with our directly link 6. But we have a problem here. What is the problem on this radius? At point I13, at that point, velocity is 0. Because it's the ground, 1, always 1, 1, 2, 1, 3, 1, 5, 1, 20, 1, 1000, except the infinity one. They are indicating the velocity at that point. If you are standing at that point, your velocity is 0. Linear velocity, no velocity there. Your v equals 0 there. Clear to everyone? So our problem is on this, our objective is to find the velocity at that point, correct? So, but this radius, velocity at that point is a 0, I15. But if we are coming down through this radius and going up to infinity distance, our velocity gradually will be increasing, and so on that radius. Clear to everyone? But the point is, as we are coming from here, our velocity gradually increasing. What is the rate of increase? It is increasing very faster angle, or that faster angle, or a very tiny angle. It is continue like that. We don't know. And that makes our problem. Why? Because when our piston, when our VA, our crank the crank is pushing the link downward, our velocity is perpendicular to link 2, right? It's this way. And it means our piston, this one will be moving horizontally to the right. Clear? Acceleration case we cannot say exactly, but velocity case we clearly say that it will be going to the right. But so we know our velocity at this point, it will be going horizontally to the right, correct? But if we can somehow limit the line, the rate of increase from here as we are going down, we can find what is the velocity here. And that is our dilemma at the moment. So that's why what do we need? We need to find how the instantaneous center, it allows us to move from one link to other link and finally to reach here. So for that, we can clearly see I13 unfortunately velocity is 0 here. Because 13, ground. And I15 also velocity 0. Look at very carefully. I15 here, the velocity is 0 as well. So if I come to that point, no linear velocity. If I go to 15, no linear velocity. And then I am looking at with you that in between 13 and 15, do we have any other instantaneous center which is not 0? And we can clearly see there is a 35 here. Can you see that? Look at here very carefully. Can you see the 35 here? 35, it means at that instant, that angle, whatever the angle we have here, at that instant, link 3 and link 5, the velocity is the same. Look at very carefully. I'm talking about classical approach. At that instant, link 3 and link 5 has the same magnitude of velocity. Where is our link 3? Link 3 is this beautiful slider. And where is our link 5? It is our this one. This one is our link 5. And link 5 has a direct connection with our link 6. We already found how to climb the tree. Clear to everyone? Because, and link 3, this link 3 has a connection with link 2, which is the velocity given our VA. Is it clear, everyone? If we can, we know at that instant here, our link velocity, link 2, so link 3 and link 5 has the same connection, same magnitude of velocity here. That I35, it means V3 equals V5. Is it clear to everyone? But unfortunately, we don't know at that instant. We cannot purely translate from here VA to that instant here. Clear to everyone? Because it is most probably link 3 and link 5. Link 5 most probably on this side somewhere here, that velocity. So we cannot translate it purely. So what do we need? We first need to know what is that 3,5 and V3 and V5 at that point. Because that is not 0. Why not 0? Because it is not a 1 index there. Clear to everyone? All the value 2, 3, 3, 5, 5, 6, 10, 20, if there, it is one is not there, and also not infinity as well. So therefore, that velocity is not zero. It is a floating velocity, we call it. Clear? So if we can somehow find the magnitude at that point, the V3 and V5, then that V5 will be using to find the limit, the rate of increase of the velocity. Clear to everyone? Okay. So that's why we are going now to the diagram. Look at here. Look at here. So there is our I-15. Here is a little bit clean compared to other one, okay? And here is our I-13. And there I-35. Clear to everyone? So here is our velocity 0. Here is our velocity 0. And that I-15 belongs to this radius of the instantaneous center, and I-15 also belongs to that radius of the instantaneous center. This dotted line, it is not a radius, it is a limit line. Clear to everyone? Your radius is this one, this line. This line, going infinity down. Don't worry about this one. This is another one. We are looking at the moment this one. Clear to everyone? So now, what I did, or what we can do, look at here, what we did. We push that this velocity VA is given to us. Is it clear to everyone? And that velocity is a link 2 and link 3 at that point is the same magnitude of velocity. Clear to everyone? Because if link 2 and link 3 equals VA, is at that point is not the same, then our link 2 and our piston will not be able to connect by the piston pin at that location. Is it clear to everyone? So therefore at point A, our V2 equals V3 equals VA, which is 9 meter per second or 9,000 millimeter per second. Clear to everyone? But is it the same? Is it a same V3 at point where is the I-35? No. Because I-35, it means link 3 and link 5, another instant they have another velocity. But we have a connection with the link 3 and link 2. So that's why we know that V3 equals V5, right? So what we did, we said, okay, but we don't know what is the velocity. So we know between I-13 and I-15 somewhere has the maximum velocity. And that velocity, to determine what we did, we put a compass here, one leg of a compass here, and then this velocity we push backward. Centering here like that. Centering here like that. Clear everyone? Look at here. Here is your I-13. I-13. And here is your I-15. And here is your somewhere I-35. I-35. Clear everyone? And you have here your link. Oh, no, this one I am putting. So you have a link. This one is. And that is your, sorry, where is that? I think somewhere here, not from there. It is from here, say, from here, this is your link 1, 2, I-12. 1, 2. And say, put it nicely. And put this one parallel. And here is your I-12 and I-14. 1, 4. Here. This is our link. And here we have a velocity. Look at there. I just put is just symbolic. You can see that one there. And now here you have a velocity that VA equals V2 equals V3. But unfortunately here also we have a V3 equals V5 at that instantaneous center. Here. Because it's on the same line. Clear to everyone? Here is the I13, here is I15, here is I35. Clear to everyone? But this is our link. At that point is our VA equal V2, V3. So on this radius, here is the velocity 0, here is the velocity 0. But here, there is some velocity, but we don't know what is the magnitude of the velocity. So what we did, but on the other hand, link 3 has a connection with link 2, because that is our link 2. And that is our link 4. Link 4. So what do we do? Look at here how I do. So I take this as a compass and I put on this side. So if I put, because here is I13 ground, I can only put a compass on a ground. I cannot put anywhere else. So compass one leg. So I put the compass one leg is here, and the other leg of the compass that you have the pencil or whatever it is. Consider this one. So I draw. Look at here how I go. I go here. Now every one of you follow me. Particularly your young man, those who are looking very angle, you cannot see it. But maybe I go on the other side. Then it will be easier. So look at here. You put that angle here because it's I13. That's why I can put a compass. And then I put my other compass with the pencil. Look at here, this one. And then I move that one with that radius. Of course, it will be radius not that way. It will be from here. Look at here. It will be like that. It will be small radius. And then you put a dot here. And then take because this velocity VA, you need to draw in scale on the entire schematic. So you take, look at here how, you don't need to even ruler. If I am there, I'll be putting my compass like that. I'll be measuring this VA and I put it here. Clear everyone? This VA, look at here, this VA, I'll not be even using ruler. I'll be taking this one, how many millimeter, and I'll be putting here. And then I will be redrawing it. But it is a 90-degree angle here. Because it is a radius. So all velocity will be 90-degree angle of it. And then I say, okay, that is this VA, I put it back. And here I am writing here, V2 equals V3 equals VA. Because I brought it back. From here, I put on the radius. And then I say, okay, that is the maximum velocity between I13 and I15. And then what I will be doing? I will be doing particularly nothing. I will be just, look at here how I do. Once I found that, I will be connecting it. Look at here. This is a limit line. And then, here, unfortunately, it become all the same line, so you forgive me. And this one, limit line. So, look at here now. Very carefully look at. This is I13, this is I15. And this is our VA. That VA I push back and I put a perpendicular to it. So it will be little bit orientation, not exactly the same as this one. It will be perpendicular to that line. Clear? And now I say, okay, from the I13, I draw a dotted line here up to the tip of that velocity. And from the tip of that velocity, up to 1,5, I draw another dotted line. It's a limit line. So what happens? Look at here. Because the entire radius of the instantaneous center, every velocity, doesn't matter if the I13 or I15 or not 120, all velocity is a 90-degree angle on this radius. Clear? So now, if I come from here, gradually, all my velocity will be decreasing and it will be 0 here. But every velocity will be like that. Every velocity will be like that. Every velocity like that. Every velocity like that, but all are 90-degree angle. All are 90-degree angle. And similarly, I can go this way, my velocity will be decreasing, that velocity, and that velocity. So it means my no velocity from the radius cannot go beyond that limit line. And that's all. And now what I do? I say, okay, on this radius, there is a point called 35, I35. So it means at that point, velocity, link 3 and link 5 is the same. So what can it happen? It can happen, I can draw a perpendicular line up to that point that is my actual velocity v3 equals v5. And that velocity I'll be using to make the limit for this one. Clear to everyone now? Because before I couldn't find what is the magnitude of link 5 velocity. And now what I'll do? Look at there. Because this I15, it is the same magnitude of the velocity here. So what I do? I put my compass here, and this I35, which I just showed you here, this one, and I'll put, if it is, look at here, it is a classical one. So here your I15, look at there, and your slider is somewhere here, for example. And here is the velocity, I15 is 0. Clear to everyone? So what I will be doing, I'll be taking now another compass, and I hold it here, and I will be, look at here how I do, compass, no angle. Because if you do angle, there is a big arrow. Small angle, you misalignment, there will be big arrow up to that point. So it is, you hold it here, and then, look at here how I do. Hold it here, and that is my other angle of other leg of the compass. I bring this one with beautiful radius up to that point. It can come here, it can go there, it doesn't matter, whatever the radius is. You don't worry about where it is coming. It can come also on the exactly same point as well. So it depends on your geometry. So now I say, okay, that is the point. Say we pay a little bit up so that it don't confuse you. Okay? So we put it here. Say we come up to that point here. Radius from here. When you bring forward, you from the tip. And when you push backward, take from the root. And that's why I took it from here. That is the rule. When you push backward, you take from the root. And when you, it's a nature. When you pull, from where you pull, like that. And when you try to push, you cannot put from the tip. You put from the root. Push that way. It's the same thing. So now, what I do with the compass, I measure my that 3.5 here. Look at here how I measure, and I bring it here like that. And then I draw of that velocity exactly the same magnitude here, and I am writing it. It is a 90-degree angle, and that is my. Oh, this pen is actually dying. So I put another pen. There is another pen. So. Okay. So look at here. That V3 equals V5. I write it here, right? And now I say from my I13, the velocity will be the rate of increase touching through the tip of this one. So I will be drawing it a little limit line. And that is, as you go down that radius, your velocity will be increasing like that. So now, my friend, you look at very carefully. If you push this one in this direction, and your piston, this one, this is your piston, it can go, velocity is absolutely horizontal, it cannot go beyond that line. And that is your VC equals V5 equals V6. You measure that length, multiply the scale that you use for this one, and you get the magnitude. That is called classical method. That is called classical method. And that exactly, I'm explaining again. Look at here. Look at here. Look at here. That's why, because at 150 and 130, 150, in between there is a velocity V3 equals V5. But we don't know how magnitude it is, where is the maximum velocity limit. So that's why link 2 has a link 5, link 2 and link 3 has a connection here. So therefore that velocity VA, we push backward, we put a one compass here and we push backward here, and it is a 90-degree angle. Unfortunately, in this drawing, it is not shown here. But in my lecture, which I do in Melbourne, I actually draw it very nicely and I showed it, because I thought that maybe it is here, but unfortunately it is not here. So I need to check it. Okay? So and you push it back here, and that velocity, you draw a limit line here and from limit line there, which I showed you here. Clear to everyone? And then our velocity V3, V5, it can go up to that point. It cannot go beyond that line. And we use that one, and then I put a compass here, and then one leg of the compass here, and the pencil leg compass, I brought the whole velocity with this radius up to that point, and here is a 90-degree angle. That is a 90-degree angle here, this one I showed you. You see how 90-degree angle here? Because it is a radius. All velocity is a 90-degree angle, which we talked this morning. Not this morning, this afternoon in the beginning. So, and then we draw a beautiful limit line, and our velocity cannot VC, when our VA can be this way, VC cannot go beyond that line. And that's how you get the magnitude of the velocity. It is only few minutes. Only few minutes. You need to have a only compass, that's all. No mathematical formula, no sine law, no cos law, absolutely nothing. If I am in your position, and that is absolutely also, it has no error thing, unless you make some mistake or alignment, that's all. No, nothing can go wrong. Nothing can go wrong, because you are not using any math. Is it clear? All right, now there is a shortcut as well. The shortcut, I don't like it, but I still explain to you, depending on the situation. If you are running out of time, sometimes you need to do that. So, alternatively, another set of instantaneous center we can use for this finding the velocity at piston 6. And that is our second diagram. I call it is quick and dirty method. Quick and dirty method. I see whether I actually showed you these things nicely or not. Let's quickly have a look. I'm a naughty man, I need to see. That's the things I'm talking about. You see how I did? You see? I put that on back, 90-degree angle, and then I put a limit line, which I showed you here. Look at here. And then our 3,5, I push up to there, it is a 90-degree angle here again. So that is my V3 equals V5 at I35 here. And then what I want to do, I15 here, I put a compass, and I brought from here with the radius, I bring it up to that point, and then the same V3, V5, I put it here as well. And it is a 90-degree angle, and I say, okay, my rate of velocity will increase. Here is a 0. As we are coming out through the radius, our velocity will be gradually increasing, but it will be tipping, the rate of increase will be passing through that tip. So that's why I draw a limit line. Can you see that? So therefore, any velocity on this direction cannot go beyond that line. Cannot cross beyond that cross that line. So my VC can only go up to that point. That's all. That's the line I was talking about.
Can you repeat one more time how we go from 6 to link between the 6 and 5?
Because link, look at here, link 5 and link 6. Link 5 has a two side. One side to that direction, and other side with this direction. So here, V6, V5, it means that end at that point. It's a very good question actually. Very good question. So here our there is a V5 and V6 is we mean at that point. And our V3 and V5, our line link 5 at that point. Because that is the nearest one to our link 3. And it will not be the same, different. Clear? At that instant, at link 3 and link 5 will be the same magnitude of velocity. And that magnitude is this one. Is it clear? And link 2 and link 3 has our VA. Because when our link 3 it moves and in relation to our link 5, that's the velocity is a link 5, a link 3 here. Okay? So it is just sequentially you are doing.
So we relate 6 to 5, then 5 to 3,
Yes.
then 3 to
Yes,
have it
yes,
the value.
yes. Okay? And if you have any doubt, unfortunately you don't have enough time. Otherwise you can actually put a little working model simulation. You can freeze that system and you can say, okay, link 5 at that end, how much the velocity? Is the same magnitude as link 3 or not? Okay? And you will also find the link 3 has a 2 magnitude. One link to link 2, another one is the link 5. That cannot be exactly the same. Because if exactly same, then it will support this one also will be. Look at here. Here is a 9 meter per second, here is a 3.4 meter per second is coming. It will not cascading all the velocity for both ends will not be the same. Okay. All right. Now have a look. The I call quick and dirty method. Quick and dirty method. But is it correct? Why quick and dirty method? Why dirty? The reason is it does not follow the classical rule. The climbing the tree. One branch, next branch, and next branch. What it did, it used only I12 and I26 and I16 at infinity. Can you see that? Link 2 directly connected to link 6. It is skipped all link 4 or link 5 entirely. Is it clear to everyone? In extreme rare you will find that situation. You find that situation is a very, very small number of time. And this is why I wanted you to emphasize on the first method. Because first method you can apply any situation. Even including your assignment that you are doing. You are using actually first method. You are not using quick and dirty method. Is it clear to everyone? Is it clear? So what do we do? Let's go to see quickly our our instantaneous center. What we found? Look at here. Hey, young people, look at here. Here is our I12, correct? At point O. And if you go a little bit up, and you can see with the light green color, actually not light, sufficiently dark, and that one is I26. Can you see? So link I26, I link 2 and link 6 has the same magnitude of velocity at that point. But that velocity is not the link to whatever the magnitude at the moment VA has. It is different because it needs to synchronize with the link 6 cascading, but skipping many links. So what happened? Here is a I12, and this line, unfortunately, it is a I16 at infinity. Can you see that? So it means as you go this way, your velocity here is a 0, but thereafter, as you move, a velocity will increase. Rate of increase we don't know. That's why we don't know at that instant, at that point, that I35 is that point, young people. This is a 35 here. I26 is here. So at that point, we don't know what is the velocity here. So for we need to find a limit line. And for limit line, what we did? Look at there. Limit line, what we did? This is our VA, which is a link 2 and link 3, and link 2 also has a connection at that point. So therefore, we put a compass here, and then from here we bring that. Look at here how I bring with the compass. It is here, and then I add that length which I did in scale. I put that one in in absolutely perpendicular to that line. Is this one, and then I draw a dotted line, and I'm saying, look, I don't do anything. It is the same velocity, V2 equals V3, which is here as well. V2 equals V3. Clear? And then I say, so the rate of increase of the velocity on this radius as we go higher and higher and up, it will be increasing, but no velocity can go beyond that line, can cross that line. So at that point, is a velocity is a 90-degree angle to our radius, so therefore its velocity can go up to that point. And then we use the same scale we measure that length, multiply with the scale, and we get directly V6. And it is the same 3.4 meter per second. Is another method. Okay? So both method first of all, you try to grasp the first system, and and your assignment also you can use in your I-15 for your BC to find it.
The one we try is to using MMC as a position, then how about the meter, 2 in 1 graph. Meter per
Okay. Now, these two things, when you draw this schematic, it will be in your own, whatever the scale you use it. That scale does not matter if the velocity can be different scale. You don't need to use the same scale because it will be all proportional. Based on this, you are determining all of them. So it will be translating exactly with the same thing. So this scale, you do as like your velocity diagram you did vector polygon, same thing. Remember, when you did your the velocity vector polygon and acceleration vector polygon, your schematics and your velocity not the same scale, different scale. Okay? And acceleration is a different scale than even your velocity.
So I got doubt here. How to
Yeah.
also.
So it doesn't matter. Because it will be translating based on this scale subsequently. But position need to be proportionally as it is. Alright, with this note, I want to stop and you can have a look at home, and I'll be uploading all of them in the Canvas later today. So all of you, what you need to do, young people, download it, go through it, see it, and if you have extreme circumstances you don't understand, of course, then you send me an email. Is it clear? And with this note, we stop here, and then our last topic we'll be talking. That is, let's go to find it. Balancing. And balancing, as you will be visiting Melbourne, this subject, any subject I teach, there is a lab. I always want a student to learn theoretical knowledge and apply it to practice. And that practice is through lab. So in engineering dynamics, I used to have 2 labs, still I continue. And also, you are in mechanics of machines, 2 labs. And both of these labs, all 4, you will be doing during your residential visit in Melbourne. When you are going to Melbourne?
January.
Oh, not very far. January when? Okay, it's already decided, right?
Yeah.
Other benches are there.
Very good. So now, your program, your program coordinator is a BBM, right?
Yes.
Yeah, she was my student, so she knows. I used to teach her exactly like you. She did, I think it's a hard time. She was a little bit lucky. I did not only mechanics and machines course review workshop with her, with her group, and also with the engineering dynamics as well, and also fluid mechanics. Okay, because you did solid mechanics and fluid mechanics too, right? And there was a course review workshop or not on that? Not a good. Because we had actually 2 people used to do course review workshop. Solid mechanics part separately and fluid mechanics part separately. And fluid mechanics part I used to teach. Okay? And your engineering dynamics as well. But later on, because of my too much workload on teaching, that's why I said, look, it is humanly hard for me. And the most important thing is that Melbourne, I teach a very big subject. And your engineering dynamics course is a 330 students. Hey, young people, listen to me. 330 students in engineering dynamics. I take the lectures, I take the tutorial. And your course, this one is a 380 or 390. This year it was, not 390, 290. I just finished exam and finalized the marks and put in the system. I came here for this subject. So, and unfortunately next year it will be even more. So I am really worried because we are aerospace engineering students also coming with our engineering dynamics. So I thought that I can give some to aerospace engineering students, teacher. but apparently they want to put on my shoulder. So I am a dead man. There is a 500 student I need to go through, and very sad. But anyway, not sad. Look, one thing. I tell you one thing. These two subjects that I teach, I do not need any writing, any book, or anything. At any situation, coming from the plane or coming from the train, I can directly go to the class. And when I am with a student, I never be tired. I never. And that is my most glorious time when I am with a student. My 100% focus to you. I never entertain anything. Even I never entertain any phone call. I said once I am in the class, rest of the world does not exist for me. Only my student. And that's the thing I follow in Melbourne, in Singapore, in Hong Kong, when I come here as well. And in my entire academic career, last 22 years, 24 years, in only one class I was 15 minutes late. Usually I go half an hour before and hang around in the class. And that's also I follow. Because, and also I go at the end, when you all of you finish, leave the room. Okay, so it is my commitment to a student. I become an academic university. It is not for money. Otherwise, with my knowledge, the knowledge that I have, I can earn significantly more money in other work. So RMIT University, as a professor, whatever the salary I get, it's a very high salary. But that salary, for that salary, I am not RMIT. I am not working at RMIT or university for money. Otherwise, as I said, with my skills that I have, luckily, I can earn in other professions significantly bigger money. All right, now come back to here. Why my passion for you? Now have a look. When you come to Melbourne, you will be doing 2 labs, and one lab will be static. Dynamic balancing, rotating massive balancing. There are 2 types of balancing: static and dynamic. And you also will be taught a little bit when you come there. So I don't want to spend a lot of time for you. Just give a little bit of preamble, and then we'll move on to the hardest part, which they will most probably will not explain to you a lot. So that one I'll focus. Now have a look. Static balancing, we need only 1 plane. Dynamic balancing, we need 2 planes. It means, look at here. If it's a static balancing, look at here. If in the pivotal point it wants to go there, we want to put equivalent force opposite direction, so it will be always same orientation. Clear to everyone? Where you live. But it is not rotating. Static balancing is when objects are not in a motion, simple way, either linear or rotational. But our machinery is subject to rotational motion or linear motion. Clear to everyone? As a result, we need to balance it when it is in motion. And that's why our dynamic balancing is more important than the static balancing. And if it is statically balanced, it does not necessarily mean the dynamically balanced. You will also see it in some videos they will be showing you in Melbourne. Okay? And the handout that you will be getting for these 4 labs: static and dynamic balancing, wiring of shafts, and also your mass moment of crankshaft, mass moment of inertia of a crankshaft, and also the projectile motion. All these things, lab manual is written by me. So when you see everything, it is written by, and then we replicated my standard in other lab as well. So you will find that things. Now come back to here, young people. So dynamic balancing is more important. But now dynamic balancing, another important thing is there are 2 types of balancing we look at in our subject. One is called rotating massive balancing, another one called reciprocating massive balancing. The reciprocating massive balancing example is in crank connected piston, in an engine, internal combustion engine. Can be single cylinder, can be 4 cylinder, can be 8 cylinder, and it can be also not only one inline, one plane, it can be also under angle as well with a common crankshaft. Okay, so that's to be engine. So let's go, we'll go through a little bit and then I explain to you and some of the interesting thing. So now rotator massage balancing, we'll be using this formula, young people. You will find the same writing also in your lab manual when you'll be doing, and I'll try to see when you are coming in. You said in January, right?
January.
Yes.
January when?
13.
Okay, so when you do this lab, I'll send either my PhD student or maybe I'll drop in for a few minutes. I'll explain to you again these things. Let everyone in the lab, and also you see when you do these things, and I'll be referring to this equation. So I'll not spend a lot of time on that. I will focus on that other one, but you just one young people, give me a little favor. Do me a little favor. When you come to Melbourne, you send me, one of you send me an email, your exact date, and then I'll be looking at when you do this lab, and I'll be dropping into your lab.
After we reach there only we know.
Yeah. So when you get and you see, a timetable will be given.
So I'll give
And and you see the date and the time. So you send me an email using my RMIT email that which date and which time, so that I can come on that time. I don't want to come other time because I may be going to the city campus or somewhere. All these things will be in Bandura campus. So that's why you need to do it if you really want to get a little bit help. So, but this one I mentioned everything correctly, and you can see that things. And I also put couple of example here, and we will not talk about these things graphical, and also I'll be explaining during that time. So let everyone, hey, I'll be explaining this one, but of your curiosity, you can go through these things. And also, every one of you have this one in your canvas. But here is a little bit of like a book. But it was in canvas after every week, under every week, we put some chapter from here. So if you print out, download all of them, and you collect them together, it will be like this. Clear to everyone? Long time ago, we used to give our student, it is to our library, and then the library used to print it, and they used to charge them with the printing cost, no profit or anything. But now everyone like digital, that's why we split it, and then we put under your week by week in your modules. You can find there is some PDF file. Have you seen that? It is actually from here, from this book. Okay. So now I want to focus on your reciprocating massage balancing, this one, because it is extremely likely that nobody will be explaining to you that there. Hey young people, look at here. Reciprocating massage balancing is mainly our piston. Look at here very carefully. If you buy a brand new car, I saw a lot of brand new car in Singapore Road. Okay, but I don't know how many of you these things. But as I have a little bit of curiosity of the car, so when I walk, I also look at even when I'm in the intersection, I look at which brand of the car is moving, because most of the brand I know. I did not have the car by myself, but I know what their things that they're doing for various other reasons. So therefore, I look at. Now the question is, when you buy a brand new car, I'm not sure how you buy in, what is the process of the purchasing in Singapore, but in Melbourne, Australia, or Sydney, it doesn't matter which city, usually when people buy brand new car, they go to the car dealer shop. And then, if you buy a brand new car, then they give you a demonstration right. So you can take the key of the demonstration car, same model, and then you drive some half an hour or 20 minutes or 10 minutes, and then you can feel how you are driving, whether you like it or not, and whether it is comfortable for you, and then you decide. Not necessarily you need to buy it, but if you don't like it, you say, I go with other model. See. So we call demonstration. So when you buy a brand new car, young people, and that car, if it is shaking like that in the seat, will you be buying that car? No. What will you be doing? How many coffee they give you doesn't matter. You will be coming back and you give the key and say thank you, goodbye. Hey, you don't want to shake in the car, right? Why the shaking is coming? Shaking is coming from three things. One is road tire input, because our road surface is not absolutely flat, so therefore it will be vibrating. That will be put there, and the other one is aerodynamic, various other things, because fluctuating of the air also pushes down pressure, but that is a minor. And the other thing is your engine. Your engine, but engine what? Not block doesn't create a big vibration, because block is stationary. Only the moving parts of your piston. piston, crank, connect, and the crankshaft. So now our objective is to find, is there any imbalance forces there? And that forces, if it is, how we can balance it? And the other thing is, if we cannot balance it, how we can hide it? If we cannot balance it, then we need to hide it. And when we hide it, so when the people who wants to buy the car, they do the demonstration drive, they will not feel the shaking. And thereafter what happens, that's a different thing. I'll be coming to that in a second. Is it clear? So there are three types of engine we usually use. One is called inline engine. Most of the cars you see in Singapore street, they belong to this class. Because you are not driving at 4000 cc engine car. 4,000 cubic centimeter volume of the engine cylinder volume. Clear to everyone? You are not driving in very rare, because you don't have space to drive that very big speed. That's the one thing. And usually any engine power is more than 2,800 cc or 2.8, sometimes they call stuff, I don't like that word, 2,800 cc or 3,000 cc, then we try to move to B engine. Why? Because in the crankshaft, if you want to increase the power of the car, of the engine, then what you need to do, you need to put more cylinder at. So in one crankshaft, when you put a lot of cylinder, then what happens here, it can have a bending moment. And you need to make crankshaft very big. You don't want that. That's the one problem. Other problem is, most of the engine, we are very compact. If you open the bonnet, you can see the engine is not very big, small. Why? Because we have to fit a lot of other things. And if we put engine orientation, that most of the engine orientation is laterally to the road lane, this way, not longitudinal. Why? Because we have some dimension problem, dimension restriction of the car. So we set up in that way. So if we make a 6-cylinder or 8-cylinder engine in a one inline engine, if we do, then our crankshaft become that big. And if crankshaft become that big, it's extremely difficult to fit within our limited space inside the car, inside the bonnet. Clear to everyone? That's the one space limitation. The other one is, when we put multiple cylinder in one crankshaft, we need to put multiple support in between, which I don't want. Because in crankshaft is a journal bearing. It's a very, very complicated system. It is not a simple, it's a fluid and other things also involved. So therefore, we want to use two support on the two end. So, and it is good for a smaller engine. If it is a long crankshaft, it is not good at all, because then it will be tilting moment like that. Not only shaking like that, it will be also bending moment. Clear? So we don't want that. That is the purpose. Why we are moving from inline engine with the bigger power to B engine. What is the B engine? It is the same crankshaft. We use two inline engine side by side. Clear to everyone? So this way we can fit multiple cylinder instead of making the crankshaft longer. That's the main purpose. So why it is a V engine? The word, because you were looking at axial direction, that thing looks like a V. That's why it's called V. The angle could be 90 degree, angle could be 120 degree, angle could be 180 degree. If 180 degree, that means this bank is absolutely horizontal to the right, and this bank absolutely horizontal to the left, and that is called opposed engine. Clear? And I will show you now about how to look at this inline engine. So inline engine, let's go, I write it here. Inline engine, if you most probably done an assignment in engineering dynamics course when you started, there is an assignment, you had some, I believe that one was the pulley rope mechanism, one assignment part A, and other section was your crank connector piston mechanism. You need to derive the equation and to simulate it. Correct? So what you did there, young people? Anyone can remember? I write down for you. A crank, connecting rod, piston mechanism, and this is our O, A, and B, and our OA equals R, and radius of the crank, and this one is crank angle theta, and then we have AB equals L, connecting rod length, and you try to find the velocity VV of that, and you also try to find out acceleration of the piston, correct or not? That's the things you did in assignment. And anyone can remember what was the equation you derived? There was the equation, you did also all this differentiation and all these things, and you found finally. And now look at here. That equation was AB equals omega R omega square. Look at here very carefully. Look at here very carefully. Cos of this one, theta 1 plus phi. That one. And then plus R by L cos of 2 theta 1 plus phi. And that was your equation. 2 phi. My apologies. 2 phi. But actually you wrote not a phi, you wrote this equation. I do a little bit good for you. You wrote AB equals R omega square cos theta, and then R by L cos of 2 theta. That was your equation. That's the equation you derived. If you don't believe me, if you don't throw away that piece of paper, you can look at there at home. You R omega square. Omega, it means that angle, that rotational velocity omega, that one, and theta is that angle, and R is your crank OA, and L is AB, that. And now what is it? It is an acceleration you have on piston head, correct? And now young people, have a look. If I want to know what is the vibration force on that piston, what is the vibration force, shaking force, I can easily find out. How? F equals, I need to find the mass of this piston, nothing else. I'll be multiplying the mass of this piston with this acceleration, and I get m r omega square cos theta plus r by L cos of 2 theta. That's all. M is the piston mass, but piston has not only piston has a 3 ring, and piston has a piston pin, everything together on the head. So therefore it will be F equals capital M, is that we call effective mass, which includes not only piston mass plus piston 3 ring plus piston pin, which is the connecting with the connecting rod. And that you write R omega square cos of theta plus R by L cos of 2 theta. That is your equation that you supposed to get in your engineering dynamics. And I usually tell a student, do not throw it away, because you need it in your balancing of the reciprocating masses of the car. So that's the mass you try to balance it. Clear to everyone? Your objective is to make it 0. But we cannot make 0. Our radius we cannot change. Our connecting rod length we cannot change. We cannot change the mass. So we need to manipulate with the angle of the firing order. Clear to everyone? So that's the things. That's for one cylinder engine. But we have minimum 4 cylinder, because 2 cylinder engine we don't use anymore. Long time ago we used to use, but not anymore. So all the cars you see in Singapore road, they are predominantly 4 cylinder inline engine. Okay, so let's go to see how we balance it quickly. So these are the engine. I'll be putting all these things for you. You will be having it. I don't want to go the detail of that. Now, this is the things you did in your engineering dynamics course. Young people, that's the things I was talking about. Hey, have a look. Have a look. That is the formula which I have written for you. Look at here. Did I write anything different? Yes or no? Oh. So this formula is in my head. I didn't even look at your presentation or the PowerPoint slides. It's all in my head. So how I remember? Look at here. Look at here. See? That's the only formula you need to know in the entire course. Look at here. M R square. Sorry, M R omega square. Like a telephone number. M R omega square. Don't change the order. And then cos theta plus R by L cos 2 theta. R by L cos 2 theta. Don't say RL. R by L, because it needs to be sequence, rhythm. And that way you remember. That's the only formula you need to remember in your entire mechanics and machines course. Because that's why we don't need any formula sheet. In your exam, you don't need any other things apart from this formula if that question is coming related to that. So this formula, unfortunately, is only for one cylinder. We need to put our 4-cylinder engine. We need to adapt it. So what do? And that's why we are, look at here. This mr omega square, if we multiply with the cos theta, we call primary shaking force. If we multiply this one with this R by L cos 2 theta, it will be secondary shaking force. And look at here, I put a common in the front. And when you multiply here, it will be mr square omega. Oh, my apology. I need to put correctly because otherwise you will make a mistake. It will be capital R. Same R. Okay? It is not a different R. This R. Okay. R is the radius of the crank. So look at here how I did. Here. So this is our basic formula. This you learn from your engineering dynamics. And I wrote everything, and then this is your shaking force acting on it. So when this one you multiply with this, it will be your primary shaking force, and this one when you multiply with that, it will be your secondary shaking force. So when you have it is for one single cylinder engine, and then when you have multiple cylinder engine, we need to put theta 1, the first cylinder in the angle, this one crank with the central axis, and then subsequent crank angle this one. I'll be talking about the phi in a second. I'll show you how we do it. And then look, this equation become, now look at here, instead of theta, you put theta 1 plus phi, that which I written here, first one. Can you see that? And then immediately I realized that I am one step ahead, not explain to you the single cylinder engine first. That's why I wrote it separately. Clear to now? And then this one will be 2 theta 1, because it was a 2 theta, remember? That's why it will be 2 theta 1 and the 2 phi, double, whatever the angle. And now look at here. It becomes theta 1, cos of theta 1 phi and cos of 2 theta 1 2 phi, correct? So cos, and this one is a one angle, this is a different angle. So therefore we can split it. Cos theta 1, it will be cos theta 1 cos, and then cos phi minus sin theta 1 sin phi. Clear to everyone? That's the exactly I did here. That's the trigonometric formula you did in high school. And here it will be cos 2 theta 1 and here cos 2 phi, and it will be here that sin 2 theta 1, sin 2 phi. Now here, we generally have multiple phi. If each phi is for each cylinder. So generally we also put a sum here. Arithmetic sum. It is not a vector sum, pure sum, multiple sum. I'll show you in a second how we do it. So this is your basic formula. Now have a look. In this formula, if we somehow can show that this sum of cos phi, sum of sin phi, sum of cos 2 phi, sum of sin 2 phi, if 0, then entire parameter will become 0. Clear to everyone? And that's the things we'll be looking at each of the engine. So now let's go. This is a 4-cylinder inline engine. That example, we'll be doing 2 examples. How much time we have? That time is more than enough. More than enough. We'll be doing, and other I'll be putting in the in the PowerPoint presentation. The process is, young people, exactly the same. No difference, and you don't need to memorize anything apart from that beautiful little formula. That's the only formula you need to remember in your entire course in the exam. And I'll be also talking that what are the things will be in the exam, so that you can prepare better. Okay? And every topics you learn, I do not need to test in exam, because some of the things you are also doing through assignment. Is it clear to everyone? So assignment is also assessing your skills in those particular topic. So therefore in the exam, I don't need to put every topic. I'll be putting only the important topic. And those important topic, you already realized: the graphical velocity acceleration, instantaneous center of zero velocity, and the balancing. These are the things will be, and there will be one question from somewhere else. I'll be also telling about that. Okay? So now have a look. This is side view of a 4-cylinder inline engine. Most vehicle on road, and not only in Singapore road, most even on Australia as well. In Europe, most car are 4-cylinder inline engine because they're economical. You don't need to put a lot of things. Fuel consumption is very little, so you need, that's more than enough. And they are usually equally spaced. All cylinder throughout the crankshaft equally spaced. You will be doing also lab when you come to Melbourne as well. So now, if you look at from the axial view, you can see the firing order of a 4-cylinder inline engine. The first crank, this one, and the fourth crank, they are in one direction, and your second and third are 180-degree opposite direction. Clear to everyone? That is the firing order. And now, what is our theta 1 and what is our phi? Theta 1 is the first crank, this one. This one, the crank angle with the central axis, which is aligned with the piston line. Clear to everyone? The example that we did, that it means that first crank, you can take this one, and the central axis with the piston is that axis. So that one is anti-clockwise. Another thing, I'm not sure how many actually you noticed how I showed the theta angle. Did you see how? Anti-clockwise. I did not do this idiot thing. I did not show you like that theta. Did I do that? What I did? I started from here, and with the arrow I finished there and I put a theta. Clear to everyone? There is a lot of messes in my writing. All the theta is measured anti-clockwise from the central axis of where this point and this point align. Is it clear? Okay, so young people, this is our first and fourth is aligned here, and third and second is here. So this is our 180-degree opposite, and we are looking at the axial view. Same line as your crank. Clear to everyone? So here, the first crank, from here up to that point, that will be our theta, and then our phi will be with the first crank and the subsequent crank angle. They are measured clockwise. So unfortunately, first crank and first crank is the same location. So therefore, our phi 1 equals 0. And then, unfortunately, our phi 4 with the crank number 4, that also in the same orientation as our crank number 1. So our phi 1 and equals phi 4 equals 0. And then phi 2 and phi 3 are here. So that's why, look at here how I did. From here, I bring up to that point, that is our phi 2 and phi 3 equals 180-degree opposite. Clear to everyone? And that's all. So I also wrote everything for you, young people. Look at there. How we measure. Theta is an angle between the first crank and the vertical axis, in our case vertical axis. And drawing that I did is horizontal axis, doesn't matter. And it is measured anti-clockwise, and this is measured clockwise. Everything written very clearly. And then you move on. And here I reorganize the equation which I was discussing. Can you see? For multi-cylinder engine, I am now adapting this equation that you learned from engineering dynamics, the basic equation. And now I am putting, this one is called primary shaking force, this one is called secondary shaking force. And how we do it. So primary shaking force can only be 0 where sum of cos phi, sum of sin phi equals 0. Why sum? 5? Because we have a multiple cylinder. And it's an arithmetic sum. It is not a vector sum. You just add phi 1, phi 2, phi 3 like that. So, and the sum of cos phi, sum of sin phi equals 0. So, sum of that first one, if this one, here, this one and this one equals 0, then primary shaking force is 0. If sum of cos 2 phi, sum of sin 2 phi equals 0, then our secondary shaking force will be 0. So that's the force there. But they can also tilting moment. And tilting moment, we do nothing. We just add axial distance in between here. And it does not double it here. It is the same A because the distance is not different. And usually the distance, axial distance is measured from the orientation of the first crank. Look at here, from here. I also showed it here. So reference line is going here and your A is started from here. So from here, A1 equals 0 because as crank 1 is reference line is the same line. And then your this one is our A2 and here up to that point is our A2 100 millimeter. And then this one is your third crank 200 millimeter A3. And then A4 will be this one will be 100, 100, 100 is a 300 millimeter. Clear? Because all crank equally spaced, equal distance. Otherwise, there is huge vibration will be, and we don't want that. All right. So now, for a moment equation, nothing else. We just add sum of A cos phi, sum of A sin phi, sum of A cos 2 phi, sum of A sin 2 phi. If we can show this one is 0, then our moment also 0. So I have wrote everything here. An example. Example. We just write equation first. That's all. We don't need to know any value of the mass of the piston and the crank radius and the connecting rod length. We don't need to because they will cancel out automatically when you put equation reorganize. I'll show you how. Look at here. My objective is sum of cos phi, sum of sin phi, sum of cos 2 phi, sum of sin 2 phi to C. Then if I can show these all are 0, our balancing system we don't need. Our engine is primary shaking force, secondary shaking force is balanced. And then primary shaking moment to show the 0, we need to write sum of A cos phi, sum of A sin phi, sum of A cos 2 phi, sum of A sin 2 phi, which is next slide is there. So how I do, you need to remember this process, nothing else. And it's 100%. No student can make mistake because it is no complicated thing at all. What is that you do? Look at here. Sum of cos phi, what is it? You just sum them up. Look at here. Cos phi 1 plus cos phi 2 plus cos phi 3 plus cos phi 4. Is it a difficult thing to remember? No. And what is our phi 1? 0 degree. What is our phi 2? 180 degree. What is our phi 3? 180 degree. And what is our phi 4? 0 degree. And it is also shown in your schematic diagram as well. So you need to put the value here and you found this great value is 0. And then sum of sin phi, look at there. What do you do? Nothing. Same thing, only the sin instead of cos. Sin phi 1, sin phi 2, sin phi 3, sin phi 4. And then you put the value here, phi 1 is a 0 degree, phi 2 is a 180, phi 3 is a 180, and phi 4 is a 0 degree. So all are 0. Sin 0, 0, sin 180 also 0. So our sum of cos phi, sum of sin phi in a 4-cylinder inline engine is a 0. What a beauty. Our primary shaking force is 0. But still we should not be very happy because we need to see our secondary shaking force as well. So for the secondary shaking force, look at here. What do you need to do? Double the angle. Sum of cos 2 phi, sum of sin 2 phi. Is it clear to everyone? Sum of cos 2 phi, sum of sin 2 phi. Instead of sum of cos phi and sum of sin phi, that gives our primary shaking force is 0. In the formula, if you put it here, it will be 0. All parameter will be 0 because it is 0. All parameter multiplication will be 0. So now, sum of cos 2 phi, look at how we did. I just added A1 cos phi 1, A2 cos phi 2, A3 cos phi 3, A4 cos phi 4. And A1 equals 0. Remember, our reference line is passing through the same first cylinder, so therefore no extra distance. So your A1 automatically 0, you put it there. And subsequently A2 will be 100 millimeter because it's a 100 millimeter our second cylinder apart from first cylinder. and our third cylinder is a 200 millimeter apart from our first cylinder, and fourth cylinder is a 300 millimeter apart from our. So you are adding that 300 millimeter either 0.1 or 0.3 or 0.2, whatever it is, right? And you add them up, and it is 0. Look at here. Sum of A cos phi equals 0. Sum of A sin phi also equals 0. So it means our primary shaking moment is 0. Primary shaking moment is 0. But if you look at very carefully, young people, there are not something terribly happening. That is our moment equation, correct? But we still have a sum of sin 2 phi, sum of cos 2 phi. Did you look at that? No. Let's go to have a look. What is it? Sum of cos 2 phi. It will be cos 2 phi 1, cos 2 phi 2, cos 2 phi 3, cos 2 phi 4. What it means? It means the angle you need to multiply double. It will be double. So if it is a 0, you multiply by 2, it will be still 0. If it is a 180 degree, you multiply by 2, it will be 360. Clear to everyone? And that's the things I did here. Look at here. Look at here. 0, 360, 360, 0. Is it clear? And cos 0 equals 1, cos 360 also 1. And cos 361, cos 0 equals 1. And unfortunately, sum of cos phi equals 4. And if it is 4, it needs to be equally 0. Sum of cos 2 phi, sum of sin 2 phi, both of them need to be 0. Only one parameter 0 will not be our balancing force 0. Look at the equation. Look at the equation quickly. Look at the equation. Our need to be sum of what is that? Not this one. This is our moment equation. Yeah. Sum of cos 2 phi need to be 0. Sum of sin 2 phi need to be 0. Then this parameter will be 0. Clear to everyone? Even this one is 0. This one not. It is not 0. Clear? And we found that unfortunately our sum of A cos phi not 0. Sum of cos 2 phi not 0. So let's go quickly. You can see here, sum of cos 2 phi equal 4 and sum of sin 2 phi luckily 0. So our secondary shaking force is not 0 in the fourth cylinder inline engine. And then we also look at the moment, the primary shaking moment, it is 0, but secondary shaking moment, when we put there with the double angle, it becomes 0.6, it means 600 millimeter. Clear to everyone? And our sum of A sin 2 phi equals 0. So what it shows? It shows an indicator that our primary shaking force and primary shaking moment on a fourth cylinder inline engine is automatically 0 with the firing order. Clear to everyone? But secondary shaking force and secondary shaking moment, unfortunately not 0 in a fourth cylinder inline engine. At current firing order. All four cylinder inline engine firing order is first and fourth is a 0 degree and the third and second is a 180 degree. All doesn't matter which model, which brand, which country manufacture them. All right, so we now got it. And now we can set up now equation, our moment equation, mr omega square, this equation, and our force equation is that, and therefore this one is our 0, this one is 0, this entire parameter is disappear, and that mr omega square, mr square omega square by L, this cos of 2 theta 1, and this one equals 4, this one is 0, and on the moment equation, this one is entirely 0, and this one equals 0.6 or 0.6a, whatever it is, and this one is 0, and then when moment equals force times the resultant force AR, that is the equation, from here you find our secondary force, how far away from our first cylinder orientation. Clear to everyone? It will be in between the second and the third one, which I showed you here. Very important. Here the secondary shaking force that is not balanced, it will be acting on the crankshaft in the midpoint. And that midpoint will be pushing up and down like that. Clear to everyone? And that will be making shake. So we found that using that equation. It is pure arithmetic, nothing, no vector, nothing. You just put the value and then find it. And other thing will be cancelling out. The mr square will all cancel out. So now here, hey young people, look at here. Four cylinder inline engine. the secondary shaking force that is not balanced, it will be acting in the middle of the between two supports, or in other word, between second and third cylinder in between here, in the midpoint. And now my question to you young people. You, when you buy a brand new car, spending a lot of money, and you do a little drive test, and if you are sitting in the car and that car, brand new car, is shaking you like that, will you buy that car, young people? No. You will immediately say, oh God, brand new car is shaking like that. When it becomes old, I don't know what will happen. Correct? And now my question to all of you. Let's go, we brainstorm together. Do you think that secondary shaking force of car which you see on the road, in our Singapore road or our Melbourne road, you think the secondary shaking force is balanced? 95%, even more than that, 95%, even 98% case, that shaking force which is in the middle of your crankshaft is pushing you up and down, double the speed of the crankshaft, because it's the 2 theta, 2 phi. Remember that, the angle? Double the speed. It is shaking you, and when you want to buy a brand new car and you don't feel anything, what happens with that? We call engineering cheating. Engineering cheating. What is it? And for that, many of you unfortunately don't have a car yet, but you will have. Because all of you are to become an engineer. Engineers are really highly professional people. And they reasonably anywhere in the world they are financially well to do. Okay? Maybe not super rich, but you will always be able to feed yourself. Okay? That's the most important thing. Don't need to worry about that. Whatever you want doesn't matter. So now, look at here. If you open the bonnet of a car or the engine, how the engine is mounted with the car body? 4 joint. One here, another one there, another there, another there. We call 4 engine mount. And young people, next time, when you open the bonnet, look at there, what is actually on that joint. You will find that thick rubber damper. Hey, young people, I told you that we are cheating. We engineer, because that car is everything designed by one of you or multiple of you. They are not from superhuman, and most of them are mechanically engineered, believe me. So it is one of our colleagues, one of our friends. They are designing these things. So they were asked by the boss, hey, our brand new car cannot have a shaking, you need to hide it. That's why we developed that damper we put in the engine mount. Very big, thick, very, very effective. Oh. So when our engine is shaking like that, because of our secondary shaking force, and our 4 rubber damper on the engine mount, which is going to the car body, it is reducing. Brand new car, almost close to 0. But where these rubber damper are located, young people? They are located very close to the engine. So when you run the engine, and your engine inside the combustion chamber is very, very big heated, 1400, 1600 degrees Celsius. You need to cool it. Even outside this temperature is at least you cannot touch it, the engine, when the engine is running. It's so hot. So, because of the hot, your rubber damper, what it does? It expands, right? When you hit the rubber, what happens, young people? It expands, it becomes soft. Correct? Yes or no? And when you shut down the engine becomes cool. What the rubber damper is now doing? They will be losing the heat. They will be now hard. So now have a look very carefully. All of you have done the material science and also solid mechanics. So during heat, your rubber expands, becomes soft. When you shut down, it becomes hard and shrinks. Expand, shrinks. Expand, shrinks. What happens as a result? We call fatigue. And as time passes by, it does not anymore. It doesn't anymore reduce the air vibration. Clear to everyone? But by this time, already 2-3 years is gone. And after 2-3 years, can you take that car back to hey, your car is vibrating too much, I cannot sit properly. Will they take your car back? No. So that's why we need to, that's why most cars, unfortunately, left unbalanced. but you will find out very later. Even I find I have two cars. One car is my Hyundai, which is a 4-cylinder engine. Other one is a V6 engine, which is a 4,000 cc car. So now, before we finish, young people, just give me a few seconds. Now, but there are some people with a lot of money. They want to buy a 4-cylinder inline engine car, but absolutely balanced. For example, Lexus. Lexus car is very expensive. Porsche, very expensive. 3, 4, 5, 10 times bigger than the other time. So what they do, they ask engineer to balance it. So how we balance it? Secondary force, I show you.
Hey.
Now have a look. 1 second, we'll finish it quickly. Now have a look. If we need to, hey young people, look at here. If a luxury car, their person is less than 1%. Remember that. Luxury car, they want the secondary force to be balanced. So what they do, how we balance it? Hey, quickly, we finish in 1 second. We put two eccentric cylinder, not cylinder, the gear. And these two gear, the mashing point, exactly the same location where is our resultant force of the shaking, secondary shaking force. And these two need to be driven by the helical gear, taking the power from the crank. Now remember, all the power you get from the combustion chamber, your objective is to rotate the wheel, forward or backward, that's a different thing. But you need to, right? And now some of the power you are adding to rotate these things. So what it does, when your shaking force is going that direction and this two force is trying to pull it down. So we cannot put like that. So therefore we make a forces parallelogram, and diagram of this one is the same equivalent force of this one. Clear to everyone? And that beautiful balancer is called Lancaster balancer. And this balancer is not a problem. Only problem is it increases the weight of the engine from 5 to 10 kilogram, because it needs to be under the crankshaft. Clear to everyone? And any engine, most of the car engine, 4-cylinder engine weight is around 70 to 80 kilo. And you add another 5 to 10 kilo, your is already 100 kilo. And 100 kilo, it means your rolling resistance will be bigger. And to overcome the rolling resistance, you will be burning more fuel. Is it clear? On the other hand, to drive these two eccentric gear with the helical gear, they get the power from the crankshaft. You are also losing some power. So to compensate that power, because your objective is to rotate the wheel and move forward, correct? So you are losing some power. So what do? You push the accelerator further. You burning more fuel. So what it does? Double. One is to rotate these two eccentric gear, you are losing power from the crankshaft. To compensate that, you burn more fuel. And second thing is increase of the weight of the engine and the rolling resistance you increase. To overcome that, you burn more fuel, correct? So two sector you are burning more fuel, and this fuel is not free, young people. It is your own pocket is coming. So financially you are loser, because your car will be running at least 10 years, in Australia maybe 20 years. Here I don't know how many. My one car is 24 years old. But looking at that car looks like a brand new. My 4,000 cc engine car. So now the question is, what happened? First of all, you burn more fuel. So your energy security. Singapore doesn't have any fuel, they bring it from outside, correct? You need to pay money. That's the one thing. Second thing is, you are burning extra fuel. So your CO2 emission is more environmental pollution. The third thing is that money is going from your own pocket. Instead of having coffee, you are spending there for nothing. Financial loss, economic loss, environmental loss, and then other one is that this beautiful thing you have under the engine, correct? It also rotates. So like our engine and servicing car, you also need to look at that its health is okay or not. So when you go to service, the people, the mechanic, they will be charging extra money. So these are the consequences. If we put that one, it increases environmental problem, you are burning more fuel, and also it financially loss from your own pocket. And if the fuel you buying from other country, not your own country, your energy security problem. Clear to everyone? You are burning more fuel. Third thing is technical problem. What is that? Servicing problem. Servicing problem, it means It's a very, very difficult. If you look at the engine, under the engine, you have a very little gap. And even my little hand, sometimes I cannot push because most of the car, sometimes when I was a student and also when I was a lecturer and senior lecturer at that time, I used to do all the engine overhauling by myself. So therefore, even my tiny hand, sometimes I cannot push it there. So how can you service it properly? So technical challenge. So these are the things you need to look at. So if I give any problem in the exam, they okay, 4-cylinder engine, 4-cylinder inline engine. Show what is the shaking force. Then you need to write all this sum of cos phi, sum of sin phi, sum of cos 2 phi, sum of sin 2 phi, sum of a cos phi, sum of a sin phi, sum of a cos 2 phi, sum of a sin 2 phi. And then you set up the equation. Only equation you remember that equation which I showed you here, right? And then if I say okay, in a 4-cylinder inline engine, okay, fine, primary shaking force, primary shaking moment is 0. But if I want to balance it for a luxury car, how I can do it? Then you need to draw this beautiful diagram correctly and show it. It is a schematic. There are some different brand, doesn't matter, most of them are similar. And then you need to tell, I can ask you also questions. What are the consequences of it? If we put it, is it a good thing? Good thing only for compute purpose. The person who will be sitting there. But what about our environmental cost? What about our fuel cost? What about our technical cost? You need to write 1 or 2 sentences. What are the things I said? Clear? So you understand it. It is not to test your knowledge or something. So you understand how it is related with everything. Clear? And then I show you one more thing, but I will not go through anything. And you do 6-cylinder inline engine. Exactly the same process. Only the phi will be up to 6. Phi 1, phi 2, phi 3, phi 4. You don't need to memorize any of these things. If I give that problem, I will be putting all this value for you. Clear to everyone? You don't need to memorize that things. Because our exam is not to your memorizing testing. I want to see you understand these things. Clear? So it will be one, if nothing else, you just set up the sum of cos phi, sum of sin phi, it will be 2 parameter more. Instead of ending at cos phi 4, it will be cos phi 5, cos phi 6. Clear to everyone? Exactly, you will be showing it here. You need to draw the schematic, but schematic is already in your question only. Clear? So you don't need to memorize the schematic. Schematic you can find and that you read or write. And now have a look. So we have a sum of sin phi, sum of cos phi, sum of cos 2 phi, sum of sin 2 phi, and then luckily in our 6-cylinder inline engine, all of them are 0. And then sum of a cos phi, sum of a sin phi, sum of a cos 2 phi, sum of a sin 2 phi, also 0. So 6-cylinder inline engine are naturally balanced with the firing order. And now you can say, Professor Firoz, then why we are not using a 6-cylinder inline engine in this car that we see on the road? Because we know 4-cylinder inline engine we have a problem. Secondary shaking force not balanced. Most of the car, 98% car not balanced, even 99% car. Because luxury car is less than 1%. And no car company can survive in the world only selling the luxury car. They will be bankrupt immediately. Okay? So now the question is 6-cylinder inline engine. Hey young people, I already told you in the beginning, when the crankshaft is very big, you need to put more crank, right? Side by side. And your crankshaft becomes very big. And when you are very big, what is the problem? The bending problem. Bending problem from where? Not the shaking force. Shaking force is balanced because it has also mass. Its own crankshaft own mass. Remember that? So when it is rotating, there will be whirling problem. Deflection problem. And that whirling you will be able to see in your lab, which you will be doing under this subject in Melbourne when you are coming in January. Okay? So then you will see that thing. So this is why, and that's the one problem. The other problem is engine orientation. We cannot put engine orientation laterally. We have to put longitudinally, then our car length will be bigger. And we cannot fit with the design law. Every country has a design law. That how much the car width and height, all these things will be. Clear? Because otherwise, if it does not comply with the standard in Australia, no government authority will not allow you to register the car. Because otherwise you'll be blocking the other people, the lane. Is it clear? So this is why 6-cylinder inline engine we don't use. Due to the lane restriction and the physical dimension restriction. Okay? And now I want to, I also did, but I don't want to go through with you, but it is the same process. B engine, we do like a 2 inline engine, and then we connect them. But B engine, inherently, unfortunately, it has a shaking force problem and shaking moment problem. But it has a big power. In engineering, nothing is everywhere you cannot win. If you want to win somewhere, you need to compromise something. Clear to everyone? You want a big power, that's why shaking thing we do. So now, I think with that, I show you, but you will be doing at home. Exactly the same process, okay? So I'll be uploading it, you see it. But B engine will not be in your exam. I'll not put it because it's a little bit harder for you. Okay? With this note, I stop and I want to say how you prepare your exam. Now, there will be 4 questions in your exam. And 1 question, please write down. I spend only 2 to 5 minutes. It's very important for all of you. Because I want every one of you, those that are sitting in this room,